name is Derek, and in this video today, we're going to be turning our attention to a new section for the course. So we're starting to look at applying deep learning architectures to modeling time series data. So that's data that basically is best organized as a sequence, so some sort of a series. So in today's video, we'll do briefly a little bit about some background, so what different kinds of time series are, the kinds of tasks inform time series. But then we're going to look at a particular example of doing forecasting on a time series. Okay, so let's go ahead and begin. So time series data is very common, very useful. A time series can be obtained via measurements at regular intervals. So anytime you're obtaining data, usually to do it well for a time series, it does have to be at a regular interval, right? So every minute, every hour, every day, you're doing a measurement or many measurements. Okay, so examples of common kinds of time series. So stock prices would be an example of a time series. Those can be updated every minute, or you could be looking at longer time ranges, so what the stock price was each day for this past year, or things like that. Electricity consumption, so you could look at your consumption at your house every minute, or once a day for the year. You can look at the consumption for larger units. So the hourly consumption for like a big city, to try to do predictions and things in order to be able to try and predict demand. So it's a very important task if you're a power utility. Weekly sales at stores, so any kinds of sales data you could think of as a time series where you measure daily what your sales were, or even hourly or something if you need to focus down on. Speech input. So normally for speech input, you're going to be capturing at a pretty high rate for what we would think of, but many times a second. So like 8,000 times a second. So, time series, working with it can be a bit difficult. So we will get into a lot of the best practices for working with time series. But to get good with working with time series, you have to understand kind of the dynamics of a system. So it's periodic cycles, how it trends over time. So as we'll see in our next example, it has different cycles. So it has daily cycles and it has yearly cycles. So you have to be aware of those. And it has trends, which we won't get into in our example. But for example, for global warming, there might be a trend that your average temperature has been increasing over years. Those kinds of things. So in general, to work with time series data, you just have to understand its regular range, its regular regime, and then things about how it spikes, how it sudden spikes. So in this example, there are multiple different types of task you might want to do with a time series. So the most common is forecasting. Okay, so our next example I'll walk you through is a forecasting task where you have a time series of weather data and you want to try and predict the temperature, say 24 hours in advance, right? But there are many other kinds of tasks that you might want to do on a time series. You might just want to classify the time series. So for example, one that you might understand is kind of important in modern days. So you might want to look at the time series activity of a person of something interacting with a website and classify it as a person or a bot, person, non-person, right? Binary classification. Event detection, another important type of time series task. So you want to look at a time series and detect specific kinds of events. So for example, for speech recognition, you might have an event detection model that's looking for particular keywords in order to wake up different parts of your model. Anomaly detection, so similar idea. So you want to do something on a time series where you're looking for parts of the time series that are unusual. So kind of important for fraud detection. Okay, but yeah, let's go ahead and move on. So we're going to look at a particular example and applying some deep architectures to doing forecasting on that time series in this video. Before in the future videos, we'll get into more details of deep learning models for. Okay, so for the rest of this video, let's look at a particular example of doing a forecasting task on a time series. This is just so you can kind of see how it's done with some of the mechanisms that you've seen so far, leading up to where we're going to be looking at using some recurrent layers, which are especially designed for doing working with time series and doing prediction tests on time series. So I'm not sure if I've shown this before, but this data set that we want to use is a little bit too big for me to put into our project repository. So you do have to download it by hand. So if you're using our class development environment, I'm just going to show you because I haven't done this before. So you first need to get it by hand. So I mean, you could just go to this link and download it, but you can just do these kinds of things from the command line inside of your development environment. So for example, we need to do this wget command in order to pull down this data set, which is a data set of temperature. Well, it's data set of readings of weather like every 10 minutes, I believe, from a particular city in Germany here. So that's the data that we're going to be using. So let me just copy that and show you how we would download this using the class development environment that I hope everybody's using for this class. So let me go ahead and bring up Visual Studio Code. So to do these kind of things with the command line, just open up a terminal. So normally when you're running inside of your container, when you open up a terminal, you'll be at the root of your project directory. So if we do a directory listing, we should see all of the subdirectories, like our data subdirectory and notebooks and things, right? So our notebooks run from inside of here. But I do recommend, keeping stuff in the place where it goes. So data should go into the data subdirectory. So if we go to this directory, we can download it using that command. So I'll just paste that wget command in my directory here, if you can see that, and we'll go ahead and run it. Right? So this will just download the file. So in this case, it's about a 13 megabyte size file. So we can see the zip file after we've downloaded it, 13 megabytes, and then you have to unzip it. So the unzip command will unzip a file of this type. So uncompress it and put it in there. So we don't really need this Mac OS directory. Yeah, after you unzip it, we just need, this is a regular comma separated value file, so it unzips to 42 megabytes. So it's not that big, although it is a lot of data, since all this data is just weather measurements. So we have temperature and pressure and things like that. I don't really need the zip file anymore either. So let's get rid of that. So after you've gotten our file, this notebook is going to be assuming that it's in the data subdirectory, one directory up from where that file is. So we can read it in. So our textbook kind of reads this in raw, but let's go ahead and use like a pandas data frame for a little bit of convenience here. So if you take a look at it, you'll see that you've got a total of 12 or 13 features. So you have a timestamp, and we get weather data like every 10 minutes here. We'll see. But we've got temperature, which is what we're going to use to predict. So this is kind of a regression task. So we're going to be trying to predict temperature in degrees Celsius 24 hours in the future from looking at the past 5 days of weather readings, right? So we've got other readings. We're going to use all of these in our model for our input. So besides temperature, we have pressure, dew point. I can really tell you what all the rest of these are, but all different kinds of measurements, the wind, velocity, and direction it's coming from, those kinds of things. So if you look at the weather data, this is the whole weather data. So there's 8 years of data from January 1st, 2009 till the end of 2016. So it goes to December 31st, 2016. Right? So 7 years. So this is a little bit of what we were talking about the periodicity of the cycles that you would see in a time series. So many of them have things like this. These are the yearly cycles. So you can clearly see our maximum temperatures in July, since this is a country in the northern hemisphere, and it goes down to low temperatures in the winter months. So these are around January, December temperatures here, right? But, for example, if we look at 10 days of temperature, there's also, a daily cycles as well, which is, kind of hidden from, you can't really see those in here. So looking at 10 days of cycles here, maybe a little bit not too clear happening here, but you can see them clearly here, right? So on January 8th at noon, we have the high temperature, and it drops to a low at night. So those are kind of typical, the daily cycles that you would see on a weather time series like this. So, one piece of general advice, if you're working with time series data, always, in some data exploration, look for the periodicity in your data. So, and especially you can have more than one time scale where you have periods of cycles occurring in your time series data. So here, like was mentioned, if we were, the scale matters. So if you were trying to predict the average monthly temperature, it's really kind of a trivial prediction, given if you can have a couple of years and you can focus in on kind of the month that you want to predict for, because it's much more regular on like that year scale time scale. But if you want to predict temperature on like a daily basis, which is what we're doing here, it's much more difficult. The signal is much more noisy. So we do have to do a little bit of preparation for the data. So we'll do a usual split. We're kind of splitting this by hand into a 50-25-25 train validation and test split. So we'll see that I probably didn't mention, we originally had like 40,000 and some samples in this data set. So these samples were every 10 minutes, having those 12 or 13 features that were measured 40,000 times, basically. So this is our number of samples that we have. So in order to prepare time series data for use by a neural network or a deep network architecture, you have to put a little bit of thought into it. We do need to normalize the data. So in general, it's always true for neural networks that they are going to be sensitive to having data that's in different ranges, and we do have some data in different ranges here. If I didn't mention it, but that's one purpose of the describe from the pandas. So we can see that we have data like pressure in millibars has a mean of 989. We have like the dew point is only 5, and you can also get an idea of the ranges from the minimum to the maximum. 900 to 1,000, and we have some other data that only ranges from 1 to 63. But anyway, the ranges are different. So we'll do a standard centering and normalizing on standard deviation. So for this task, we have to create a data set, we've seen these before, that will yield batches in a particular format. So we want it to yield batches of data from the past 5 days. So those will be the inputs. And we're going to downsample this a little bit. So from the past 5 days, but we're going to only take a measurement, one of the measurements from every hour instead of every 10 minutes, so 6 times an hour, right? So we'll downsample a little bit. And then the target. So whatever the last measurement is, we want to find the temperature. So these, we have 5 days of all of the different weather measurements, the 12 or 13 features that we have in this data set. 5 days of it downsampled to one measurement per hour. And then our target is just the temperature. We want to try and predict the temperature 24 hours from the last measurement that we have as input, right? So it's a 24-hour forecasting. So we've seen these dataset objects before from TensorFlow. So this is another one particularly for doing time series data. So it has things built in for handling time series. So just a quick example of kind of how this works here. If we have a sequence like this, and then we're trying to predict for things like that. So here we want to have a sequence length of 3, and then we want to try and predict the next item in the sequence. Okay, so the only possible sequences that you could have if we did that would be like this. So for 0, 1, 2, the target would be 3. For 1, 2, 3, it'd be 4. For 4, 5, 6, it would be 7, so on. Right. So that's what this is doing in here, doing this time set series data set from an array. Okay. So we give it our data set. We chop off the last 3 because we're doing prediction using time series length, a sequence length of 3 here. Right. So there's no valid data sets. So the last valid data set is 3, 4, 5, where we predict 6 here. And then we're asking it to produce batches of size 2, so we'll have 2 samples of the data set that we want to try and train with, and to randomize them, so bring them out randomly whenever we get the next batch from the data set. Right? So with that data set set up, we get the results that we saw here. Right? So we get batch sizes of 2, and that's kind of what it means. Right? So in this case, we need to get a sample length of 3, and then the next item becomes the target in this data series. So in this example, we're using that utility function from Keras to create these data sets for us from the data that we've read in from the file. We've already split it up into the training, validation, test set. So we want 3 data sets, 1 for training, 1 for validation, 1 for testing. We're going to use a sampling rate of 6, so that was kind of the downsampling that I was talking about. So we'll only keep 1 sample each hour. We're going to take sequences of 120. So since we have 1 per hour, that means we're going to give it 5 days of observations to try and make its forecast, its prediction of the temperature 24 hours from the last observation that we give it. So we have a delay of like this. So we have to add 24 to like the index for the last item in order to get the one that's 24 hours in the future, basically. Okay. So these will create those data sets, setting them up with the correct item for the raw data and target. So notice that we're only given the temperature as the target. So we pulled out the temperature feature, especially in the previous cell up there. And we're using a batch size of 256 in this case. So just to make certain that you're absolutely clear, once you have these data sets, again, you can iterate over these as if they are like an array or something, and it will produce batches for you. So if we get the first set of samples and targets from the trained data set, the samples are of the shape. The batch size is 256. The time series, we've got 120 samples, and there's 14 features, right? So 14 is because there's 14 different weather measures. So basically for every time step, for every hour when we did it, we had 14 measurements of the weather at that hour, right? When we have 120, that means that we go back 5 days. And then there's just 256 targets, which are the temperature in degrees Celsius that we're trying to predict. That's 24 hours from the last measurement in our last sample. Okay, so we're going to give a couple of examples of attempts of how we might try and build a neural network architecture for this forecasting task. We'll start with things you know. So let's start with just a basic sorry, before we do that, let's do a common sense baseline. Okay, so if you were told that you need to make predictions yourself of what the temperature will be the next day, the obvious thing to do is just predict that it's pretty much going to be the same temperature as right now, right? So if it's noon and the temperature is 10 Celsius, probably it'll be somewhere around that on noon the next day. Okay? So this is an example of a common sense baseline, right? So this is something we've talked about before. You always want to have that in mind before you start building a machine learning model, right? So, because if you can't build a machine learning model that can predict a simple approach, simple common sense predictor, then your model really isn't doing anything special. Okay. So in this case, so I won't go through this step by step, but it's relatively easy, right? So basically all you're going to do is take the last temperature in the input sample and have that as your prediction, and then measure it. We're going to be using the mean absolute error, right? So in this case, it's the absolute value of the difference, and we sum up that, right? You'll see that the common sense baseline should give exactly the same results in this case here, of about 2.62 on the test data. Okay. So that means that a simple common sense forecast is usually going to be maybe off by 2.5 degrees Celsius. Okay? So now the game is to use our knowledge of deep learning to build a model that could beat that, be more accurate than just using the current temperature to predict what would be 24 hours. Okay, so let's try something that you're familiar with. And we'll get something simple, so we'll get another kind of a baseline. So let's just try a basic machine learning model that you should be familiar with, where we'll just use a single dense layer, a single hidden dense layer, and then we'll have a final layer. So our model will look something like this, where we just have a single hidden dense layer where we'll have 16 units, and then this really is a regression problem. So our final output has to be a dense layer with 1 unit, and notice there's no activation if you remember back to how regression problems work, because we want to be able to predict a temperature in degrees Celsius with kind of any kind of a range, right? 2 quick notes on this. The data set is a little bit big, so if you're on CPU, this might take a minute, 50 seconds a minute for each epoch, so a little bit of time. Also, it turns out that something's happened since TensorFlow 2.15. Feels like it might be a bug to me. It looks like it should work with the flattened layer, so I'm not certain what happened, but the flattened layer does seem to get an invalid argument error, so something is wrong with the tensor shapes that happened. Finally, I did find a workaround, so the reshape layer does seem to work correctly. So just replace your flatten for this example with a reshape, and you have to explicitly give it what the shape should be. So the shape is going to be the sequence length times the number of features here, right? So, just to show you, if we create the model here, look at the summary. So, we end up with the same thing that a flatten is supposed to do, 1,680 outputs coming into that dense layer where we're going to use 16 units here. All right. Let's go ahead and train that. Okay, so once it's trained, we can evaluate it. You should get basically the same results shown in our textbook on this example here. I still think this model is maybe overfitting right away, so it might be helpful to add some regularization or even just reduce the number of units in the output layer. But you should get, let's look at the learning curve. You should get about a 2.6, so it's not beating our common sense baseline. It's about the same. So the best model on the validation loss, we'll usually get around 2.6, somewhere in a similar range to what we were seeing for our baseline. So, but yeah, looking at the loss, it might be overfitting right away. So you might be able to tune that a little bit better. Okay, so let's actually try a convolutional layer then that you're familiar with. So these can be useful for some time series. Basically the idea, remember that you learn that for a 2D convolution, it's learning a kernel that can reuse the same representation across an image, right? So you can use like a 1D convolution to potentially learn a kernel that learns patterns over a sequence of a time series. So, for example, learns patterns across the 5 days that are useful for it in predicting the target for the time series. Okay, so we can try that out. So I mean, sometimes 1D convolutions can work well for time series like this. So, in this model, our author actually puts in a couple of layers of some convolutional 1Ds just to try some things out. So we have the usual, like we saw when we were talking about image processing, of some convolutional 1Ds and some max pooling layers. So let's go ahead and define that model. Take a look at the summary. So the result is from our he kept the kernels the same here. So again, these things we can maybe tweak when we see the results here to try and improve performance. But we are following the usual pattern of downsampling the first dimension here, which is our the number of samples in our time series. So we'll see how this works. Should take about the same amount of time, and we will train for 10 epochs again here on our model with the 1D convolutions. So once we're done training here, you might get a little bit of a hint by watching the validation metrics that were happening while it was training. But usually this model will do worse than the previous one. So on average, you'll get something higher than around or higher than 2.9 on our mean absolute error. So again, I mean, maybe some tuning might improve that, but it's doing the way we have it right now. It's doing worse than the previously densely connected model, and even worse than the common sense baseline. So there might be some things. So again, convolution 1Ds can be useful for time series, but here the weather data doesn't quite respect that idea of the translation invariance assumption. So while the data does feature daily cycles from the data from morning follows different properties than the data from the evening. So, there's a very specific time scale it would have to learn. And there might be some so yeah, there might be some attention effects here. So I mean, really, the most recent stuff closest to when you want to make the prediction is going to be much more important. So the convolutional network just in one dimension really can't leverage. Won't be able to give more importance to stuff at the end of the time series than at the beginning. So the next model we'll look at, we'll use what's known as a recurrent layer to make a recurrent neural network. Okay, so that'll be the topic of our next videos. Try to get you to understand the details of how a recurrent neural network works. But for the moment, just be aware that basically these layers are designed to work with sequence data, time series data. So let's try one out. So there's a couple of different flavors of RNNs or recurrent layers. We'll use the long short-term memory called an LSTM layer. So here, similar to our first model, we just have a single, instead of a dense layer, we have a single one of these recurrent layers, an LSTM layer. And this parameter is kind of the same. So it will have 16 outputs from the layer here, okay? So let's define our model and add it in a summary there so you can kind of see. So again, it'll have a similar that we had before, although these LSTMs, they expect time series. So I mean, this is really the kind of thing they expect as inputs. We don't have to flatten or reshape it or anything. So and this will give 60 outputs to our normal dense layer that has no activation function. So let's go ahead and try and train that again for 10 epochs and see what the results are. Okay, so when that's done, that model will probably take twice as long, twice as much computation as the previous ones that we looked at. So you should usually find that this model does good, significantly better than the previous one, of course, but this might not look real impressive to you, but it is probably doing better on the test data, much better even than the common sense baseline we have. Okay, so I mean, just if you're not too impressed by that, for one, predicting the temperature 24 hours is relatively tough. It's a tougher problem than you might think. So probably getting much better than lower than 2.5 on test data, even if you spend a lot of time on this and tuning stuff, you probably won't be able to get much better than that, even using kind of the best known tools for this sort of prediction, right? So this small recurrent neural network is most likely significantly beating the common sense baseline, and it's relatively simple, right? We didn't have a whole lot of stuff in there, just a single recurrent layer. All right, so that's it for this video. So just a kind of a summary, reminder of what we did in here. We introduced to the using what time series are, and then using neural networks, some example of using neural networks, different types of neural networks for tackling a common time series problem, doing a forecasting. Okay, so a time series could be any kind of data obtained via measurements at regular intervals. So working with time series, we won't give you a whole lot of advice in this class about it. It's a whole nother topic in and of itself. They can be tough data sets to work with, so you have to understand the dynamics, the cycles and the different periods and things that might be in your time series to work with them effectively. So a common time series task is forecasting. That was the example that we were looking at in this notebook. I didn't mention when I was talking about this, but in the textbook it does mention it is important to always use validation and test data that's in the future from the data you're trained with. Okay, so for time series, you should never allow data that you train with to be in the future of any data that you ever use for validation and testing. So that does mean that when you split the data, if your time series is a sequence, the testing, you shouldn't be shuffling it before you do the split. The testing part has to come from the furthest step in the past, and then validation and test should always come after the data that you split off for training. And we didn't. So our next video will discuss what recurrent layers are and how they work, but we got our first taste. So recurrent neural networks are specifically designed for data that's time series like, where causality and order matters in the input. So that's it for this video. I hope it was useful for you, and I hope you'll come to our next one where we'll talk in more detail about what recurrent layers are and how they work.